and then the device where you have one of the nodes that terminal link is connected to fails, and the information is to go from one node to maybe another node that's on the other side, or that's after the second node. Because you have three nodes here. What happens? Obviously, information can't get from A to C anymore because maybe B in between uh, uh, it's not working, or it's dead, or has problems. So information uh, cannot be relayed from A to C any longer, or from node A to C. So these are some of the limitations that you might have. And even in terms of access to the resources that maybe a given node might be hosting or carrying, it's going to have competition in terms of when and how, or specifically uh, time-wise, when the information on that device or that node will be able to get delivered to a given request by a given node. Okay, so that's one thing. Limitation is one reason why you do not want to connect each and every node to every other node. The other one is creating of manageable wiring, because obviously if you were to connect the various nodes to every other node, you're going to create a lot of wiring involved. Because if assuming you had five nodes and you were just going by this approach, you realize you have to wire each and every one, and that creates a whole bunch of wires within the connectivity setup to form that network, and then that could create a huge unmanageable scenarios. Um, that's difficult to handle or to even troubleshoot or even in general terms manage. So it becomes unmanageable. Number of wires coming out of each node becomes very, very unmanageable. So ideally, you don't want to do that. I can imagine picturing so many wires coming together to form just a simple network. Like I said, I can use that as an example with just five PCs. You want to connect five PCs, and you have to basically wire all of them together without a central point, and that just doesn't look uh, efficient enough. Okay, and someday some of you are gonna be in those environment. If that environment is poorly planned, poorly managed, then there's that high probability you're going to be in some of those, or you might get the chance to experience what really uh, this really means. Okay, and the other one is cost, expensiveness, because if you're dealing with uh, a number of physical hardwares or device just to form a given just a quick connectivity for a given network, you're bound to incur a lot of cost. Uh, and it's not for most businesses that, or even for the average user, it's just not an efficient way uh, to run your organization. Okay, so we wouldn't really want some of these. Anyway, so these are some of the three, I'll probably say some of the key reasons why we do not connect each node to every other node, or we don't interconnect nodes together like that without going through various other indirect forms just to access resource or quick connectivity for a given network. Okay, so solutions where they're indicated, you have indirect connectivity using either intermediate forwarding nodes like a router or switches or gateways, or what have you. Okay? So if this happens to be, if this is a solution to address this question here, and the thing is, how do we make indirect connectivity efficient? How do we go about it? Or how does it really come about in terms of making sure we don't limit ourselves or have a whole bunch of cables that we can't manage, or spend so much on hardwares and devices. And this is where we talk about switched networks and switching techniques, technologies that that have been developed over the years to make indirect connectivity um, affordable, manageable, and basically unlimited. Yeah, the exact opposites. Okay, as a solution. Okay, so a network can be defined recursively as either two or more nodes that are connected via a link. And in this picture here, you have two or more nodes that are connected, okay, with a link to another given node in an indirect form, okay, and that switch connects to another switch that's also as creating connectivity for a couple of other nodes. And within all of this, you have one given network being formed just from using an indirect approach. And this way, this node over here can even transmit information to a node over here or a node over here via the various links and indirect mediums of connectivity. If you notice, this guy here doesn't really have like that direct link between him or this node and this node, but indirectly it has a way of getting to it via these intermediate devices. So that's what we mean by the indirects, and hence the reason why we say a network can either be defined recursively within this way, or in this form, same recursively, or two or more networks that are connected by one or more nodes. And this is where interworks or the internet is factored into the equation. So here we do have nodes, okay, that are connected to a given network, and then we're using the cloud symbol for that, and which forms one network over here, and that network is connected to other network via an intermediate network equipment or network node, okay, to help information transmission from this network to this network possible. Very good, and that's what you term inter-network. So this is another way of recursively defining a network. Okay? So yeah, recursively two or more nodes connected by physical link, or two or more networks connected by one or more nodes. Okay? So that is what a defined network is within a switched network. We still on switched network. Okay? We've not really actually delved into that part yet, how it really happens in terms of switching the various link transmissions that comes through some of these recursive network definitions. Okay? So this is what we look at now. We look at the techniques that are used for the switching. And there are two main strategies or techniques that are used to switch networks or to switch signals from networks to networks or from nodes to nodes. Okay, the first one would be there are two key switching strategies or techniques. We have the circuit switching, which carry bit streams, and then we have packet switching, which usually forwards or carries packets instead of bits. But packets also bits anyway. But in this, when it comes to in reference to circuit switching, they usually in streams. Okay, we'll look at what we mean by streams here. Like for instance, me talking, a voice stream would be a bit stream if you wanted to digitize it. So circuit switching is the key uh, strategy that makes that possible. That handles bit streams transmission. They usually require a dedicated circuit or a dedicated link uh, to enable that transmission to be possible. And the links are usually reserved to be used uh, by communication channels. So, and we do have other ways of going about uh, the reservation of the links, either through uh, a multiplexing approach, which handles the communication channels uh, for a given specific transmission, where we encode or we use time base, or we encode it using frequency base, or we use purely codes to differentiate the signals that have been transmitted or that have been switched within a given strategy. Okay, and a typical example within the circuit switching is your telephone, the original telephone network. Obviously, today telephone networks have embraced other technologies or strategies beyond just being carrying bit streams. They do carry other services as well, as you know by now. Your ISPs today, if you notice, they carry other signals or other information other than just bit streams like voice. You know, you have data as well, video content, and what have you. Now, when it comes to the packet switching part, it's not more for bit streams, but more of packets, which are more segmented bits put together to form packets, and they usually stored and forward. So they generally considered non-synchronous, whereas circuit switching, since it's been a bit stream transmission, they are considered synchronous. Okay, so you'd have information, or another way to represent it is circuit switching is more live, whereas packet switching is delayed or non-live. It's not a live transmission because the fact that the bits that have been put together into packets are usually stored and forward. And when something is stored and forward, it doesn't really become synchronous anymore. They're not live streams anymore because they've been forward, they've been stored first, so that holds up time. In terms of time, reference to time, they're not live feeds anymore, or they're not live transmissions anymore, as compared to your circuit switching. Okay, and they operate on discrete blocks of data as packets, and utilizes resources according to traffic demands. They do send and receive at variable rates, whereas on the circuit switching part, the bit streams are more at a constant rate to make sure the information is as synchronous or live as you would want it. I usually use a scenario as you talking on the phone to a friend or a colleague of yours, and when you say hi, how are you, uh, the person on the other end hears hi first, and then hear the other sentence like how are you maybe a minute or two later. That is not a constant rate based stream of information, or that is not a synchronous or live transmission, and we don't want that. We want voice supposed to be what it's supposed to stream synchronously. It can't be delayed, basically. Okay, it has to be a live feed, a live transmission, where you're hearing whatever the person's saying right away, not hearing it later, as you'd find within data packet switching, where The information is it's in packet form. They actually store them forward, and they come in various variable rates as well. Uh, until they all come together as the actual block of data, you really can have the entire information. So hence the storing forward. Okay, and the internet happens to be a good example of that. Okay, so now that you've got a bit of a uh, let me see, understanding of what really happens when you create connectivity between nodes through switching strategy. And the question is, what is next? Yeah, what is next? Oh, what is next is basically having your node device or your host devices connected directly or indirectly to each other. And we can provide either, or we can, yeah, we can provide either host-to-host connectivity, or we can make it a host to multi-host connectivity. Okay. Nodes, on the other side, nodes must be able to determine which host they want to transmit an information with or to. Okay. So that's one next when it comes to how after you handle the switching part, then you have to be able to uh, know how the host devices needs to be connected, and how nodes need to determine which of the host devices and information needs to go from to a given destination host. Okay. Okay, so now with that, on the next part of what is next after you have all your switching things done, you've already seen how the node you can have a host-to-host connectivity, and a node deciding which host to pass information to. What is the other next thing that you have to think about or worry about? The other one is addressing and routing. Addressing here represents uh, specifically how you label a given node or a given host device that is participating in that information transmission. Okay, so addresses are usually considered byte streams that are, are, are identified to a given node. Okay, that comprise of the various host device, network devices, and host devices, and they're usually very unique. Very unique. You have MAC addresses, IP addresses forming the basis of some of these uh, uh, uniqueness when it comes to addresses. Routing is how the informations are forwarded, or in terms of its general uh, approach, forwarding decisions made is done by routing. So routing's job is to basically decide on how to forward messages from one node to another or from a host to another. But generally, routing falls within network devices. Okay, so we talk about routers, maybe access points, gateway devices. Yeah, those are the key devices that are designed to handle the decision making of how information or data is needs to be processed or transmitted. So the process of determining how to forward messages to from a source to a destination requires the address, or uh, uh, calls for an address. And there are different types of addresses. Now, there are different types of addresses, and then there are different kinds of addresses. We'll get to the kinds later. But the types here are how messages are delivered in terms of addressing. So we'll look at our unicast, which are node specific, and this is where IP address plays a key role. So devices that wants to uh, transmit information from a unicast point of view would more or less be within node-specific address and types. Okay, and then you do have broadcast, where all nodes on a given network uh, is assigned an address. So whatever message is sent to that, so it's more like having a network address where information sent to that network address gets delivered to every other node within that given network. So here we say they are network defined domains. A good example I use is various shortcode messages that you get from your ISPs. Uh, uh, if say you had one ISP, it could be Vodafone or Verizon or Sprint or uh, in some other places you have Tigo, MTNs, uh, Glow, what have you. These all are all networks in their own defined realms. Okay, and if they wanted to send information to their subscribers and as bulk messages, they don't really need to have to know specific uh, node address of their subscribers' devices, but instead it can just send out a broadcast where within the network address level, and that message will be delivered to every node that falls within their network domain. Okay, and then you do have unicast. Unicasts are usually based on subsets of nodes, so they have this like uh, the segmented domain sets within a given broadcast domain that information can be sent to. Okay, like for instance, you want to form a network of your own within a bigger network, then you can have a segmented domain set to use for broadcast information. So you can send messages to just your subset domains of nodes within a bigger network. This ensures a bit of privacy if you look at it. So you don't end up circulating information to everybody. Another way to look at it is WhatsApp groups. You know, if you notice, if you create group one or group two or various other groups, you do that under what? A WhatsApp network. And the reason why you want to set up those small groups is so you can basically have your own segmented set of nodes that you can transmit information or you can broadcast or you can transmit information to. Very good. So that's another way to look at it. Okay. So moving on, a network can be constructed from nesting of what? Networks. You can build networks from just nesting of other networks, which is what the internet is really all about. And an address is needed or required to create reachability to a given network device or a given network node, or even to a given network in general. And addresses are used to route the messages towards the delivery destinations or their proper destinations, as you might say it. Okay, so to like put it in perspective, a host knows how to reach other hosts on a given network, and host should be able to allow nodes to use a given network for communication. But if host knows how to reach every other host on a network, the question is how should those nodes uh, use a network for communication. Yeah, so well, how should a node use network for its communication? Well, all pairs of hosts should have the ability to exchange a message, and it needs to be cost effective in terms of resource sharing to guarantee efficiency. So looking at how, or coming back to the question of how should a node use the network for its communication, it needs to figure out ways to share their resources. Uh, since you have a network medium and other devices and also other nodes within an average given network, you would have to figure a way, or your nodes have to figure a way to use the uh, services at a very, very cost-effective manner, since you're sharing resources basically. So pairs of hosts that are sharing or rushing information on a given network must have a way of handling that information sharing, okay, to address efficiency of the limited resource that it might have at its disposal. Um, Cost effectiveness here is usually handled by routers. So it's the job of a node device like a router to determine how a host uh, or a node would use a network for its communication, okay, as a cost-effective approach. Um, and another way that a node would use a network for its communication efficiently is by having a multiplexing approach. Uh, Multiplexing approach is where you have physical links and nodes um, sharing resources among various users, either via a time division approach or a frequency division approach. So in this scenario over here, we have two switches, and let's assume these are host devices, and we're going to call these host devices over here sending node devices, and you have destination, so sending, destination, okay, and we have three sending devices over here, sending node devices that wants to transmit information to a destination at the receiving end. Okay, so send devices receiving ends, but destination, source, and destination. Okay, let me go over this real quick again. We have source. I'm going to represent these as your source nodes, and these on this side are ours as your destination nodes. Okay, and these could be just your various host devices, PC, a router, sorry, a switch, a server, uh, service devices, terminals, and what have you, that wants to transmit information. And they have two switches with a single link that interconnects it together. Okay, and we want to use, since we want to address the question on how a host node uses a given network to transmit information. The question is, in this scenario, how would they go about it? I mean, we're saying that multiplexing is the approach to going about that. So the key here is how that multiplexing goes about its approach, or goes about its job of making sure the links are shared efficiently between or among various users that are interconnected to that given network. Okay, so we have your source and your destination, and they are all trying to what? Use one given single link to transfer information. So now we say if this guy or this source here wants to send information to say a destination R2, so we have L1 trying to reach out to L2, and then L2 also wants to reach out to other receiving nodes on the other side, and they all happen to share the same medium. Won't that create congestion? Won't that create a problem since we're just using a single link? Yeah, you'll probably say, yeah, it should create a problem, which is true, you'd be right. But with multiplexing as a defined scheme used, we are able to manage the flow of transmission feed for the various nodes that we have. So they can be able to use this resource efficiently. And this can be done either by first in, first out approach or last in, first out approach. But there are various ways that signals are multiplexed. It could be by bits encapsulations or bit synchronizations and what have you. And on that transmission link, informations like the addresses of the source and destination are well embedded onto a given node's transmission. So like for instance, if L1 wants to send information to R2, it has its source address as well as its destination address embedded in any transmission feed before it even hits the switch. So when it gets to the switch and it's being transmitted over this single link, when it gets to the other side of the switch where the other nodes are connected or receiving nodes are connected on, it'll be able to determine whose message is what based on the address that has been attached to the transmission link. Okay, so in this way, we don't lose information in transit, or we don't have L1's information going to maybe R1's information, or we don't even create a jammed up link. Like sometimes what happens when you're roads, when you have a jam-packed traffic because maybe there was an accident or there was poor road signs or road demarcations or road navigation or routing. We get multiplexing in this sense helps address that. Another thing that multiplex also addresses is it's able to encapsulate various signals, various forms of messages from voice, video, and audio from different receiving units, and it's able to transmit it through a single link without having to worry about compromising integrity of the information being transmitted. Okay, but obviously with just about any system of engineering, there are bound to be challenges. Okay, especially when you're dealing with electronic devices or electronic signal transmission, you're bound to have issues. Even with multiplexing, with the most fanciest multiplexing designs that you might have, there's still bound to be some issues here and there because you're dealing with what electrical devices or electronic devices, and at some point they're bound to give you some failures in transmission, breakages, packet loss, or transmission loss here and there. Okay, so obviously, yeah, there should be some problem. Now, some of these problems that you might encounter with within networks and its implementation, as far as maybe multiplexing is concerned, you'd have reliability, and at the top of it, reliability can be at stake. This is where you have bit errors or bit level errors where electrical interferences might occur to disrupt the number of bits being transmitted. Uh, so assuming you send a message of hi with about uh, 16 bits within any given network implementation, there could be a scenario where a bit level error might occur due to interference from electrical uh, challenges, uh, which would hamper the full bits or full 16 bits being transmitted across to its destination. Packet level errors when it comes to packets, so for your constant bit streams, for the packets wise, you can also have packet errors which creates a lot of congestions. Yes, with when it comes to data transmission at the packet switching level, uh, one of the key errors that comes across for the most part is congestion, especially when the medium has a lot of contentions on it, or the pipe or the transmission capacity cannot meet uh, the demands of the various nodes that wants to transmit information on it. Okay. Now links and nodes can also fail because yeah, physical links, your copper cables, your fiber optic cable, they can also fail. They can also break down nodes, your servers, your switch, your routers. Yeah, the electronic devices. They can have failures. Okay. So we need to distinguish between what's broken and what is flaky link, and also what is failed and what is slow. So when we talk about link and node failures, you need to understand that the fact that you have link and node failure doesn't necessarily mean that you have a dead system. It could be one of either a broken link or a flaky link, or it could be a failed node or just a slow node. Okay, so that's reliability for you. Another undesirable challenges that you might encounter with networks and as far as switching and multiplexing is concerned, performance is also another issue that might come up, where messages are either delayed or they delivered out of order, third party easing on or eavesdropping, like hackers eavesdropping into packets just to sniff them and hack them for devious purposes. And other challenges that might also come up is might be application expectations and hardware capacities that you have. Okay, so this is some of the undesirable issues that you will look at. The first one was or challenges that you can foresee within network transmissions or connectivity. It's reliability and performance. Okay, great. So on that note, we're gonna end of this note, the introductory note for now, and pick up more in depth with some of the things that we've basically covered at the introductory level, in much more in depth later. Okay. Research areas that you probably want to look at within network, as far as network is concerned, would probably be routing, security, ad hoc networks, wireless network protocols, and quality of service. These, if you really want to really get much more in-depth understanding of networking, these are some of the key areas that you probably could probably want to want to look into. Okay, routing security, uh, wireless protocols, value of service, or that. Okay. So introductory level from a textbook point of view, we we've just given a general overview of what is yet to come and much more in depth. Uh, I would advise you read within the book, within the required textbook, chapter 1 to 1.1 to 4 to 1.4. And the data communication network. That happens to be the textbook that I'm getting some of the information from, or some of the other information can be picked up from at the introductory overview level. And the book is written by William Stallings. So get a chance, go through it. Just get an overview, as we move on. On that note, we end over here and then we'll pick it up on lecture 2.